first lesson of Unit 7 is about taking what we understand about vectors and improving our ability to do algebra with them. You can see, let's just take a quick look at this unit. So algebraic vectors is kind of like a new way of looking at vectors. You already know how to do it, but we're going to kind of build up our understanding. Next, we'll learn about some operations, what you can do with vectors. We know how to add them and subtract them right now, but and we know how to how to scale or multiply them. There's two other ways to multiply vectors, what's called a dot product and a cross product, and then there's what these things actually do and are good for. So first we want to sort of really concentrate on how do you understand a vector as an algebraic object. In Unit 6 we're doing a lot of drawing, right? A lot of drawing and cosine laws and how does this vector line up with that vector and so on. And that's good, but there is another way to do it, and in some ways a better way to do certain types of questions, right? The drawing is a really good way of doing a number of them, but the algebraic vectors enable you to do things that the bearing vectors we were working with last unit don't. So one of the things that you may have noticed throughout this whole process is that whenever I was drawing a vector on GeoGebra, so let's say I just make a random vector here from here to here, it would define that vector as two numbers. Like it never gave you a direction and a bearing, or a magnitude and a direction. It just gave you two numbers. And if you think about how it's giving you those two numbers, it's like how much did you have to move in the x, and then how much did you have to move in the y, right? And that would be equivalent to this vector right here, which sends you 5 to the right and up 15, right? So you know that that's a perfectly good way of describing this vector, because vector u could be considered to be the sum of a vector here. So let's make vector v 5, 0, and then vector w 0, 15. And we know that vector u is the sum of those two vectors, right? When I add the two vectors together, I get the exact same thing as vector u. We talked about this going both ways. You could take two vectors and simplify them into one, or you could actually work the other way around. You could take one vector and break it down into two. Now, normally speaking, breaking one vector into two is not going to be helpful, except when you make those two perpendicular to each other, right? As I have done in my picture, so that really we can just think of it more like a point, right? It has a y, movement, and it has an x movement. Now remember, a vector is not a point. This vector 5, 15 has really nothing to do with the point 5, 15, although that is where this vector that I've drawn happens to end. If I started it over here, right, and then did vector d to e, this is the exact same object as the one I drew the first time. Because remember, a vector is not a location in space. A vector is instructions. It is a way of moving. It is a to B type of instruction or direction. Okay, so where the vector is drawn is not relevant, but how it's drawn, as in how long is it and what way is it pointing, is relevant. And it turns out that instead of describing that as a number and an angle, it's often easier to just describe it as a pair of numbers, an x sort of number and a y number, right? And that would be the equivalent of the vector that you are describing. So this is vectors in two space. Now, before I go any further here, the real reason you need algebraic vectors, right, is because when you start talking about 3D, which GeoGebra has a really good 3D axis for you to use and try. And to get to it, under View, I just enabled 3D graphics. Now, suppose I draw a point in 3D. So let's make a point, 4, 3, 1. So there it is. It's kind of like out in that direction and above the plane. right? Now let's say I wanted to do a vector. So point O is the origin, right? And then I wanted to do a vector from O to A. Okay? Now this vector, okay, exists, and it's the same thing as it would have done in 2 dimensions. It has it has a point where it started and a point where it ended, but they're not really part of the vector. They're just here to demonstrate. The vector is a set of instructions for how to get from point O to point A, right? And you should realize that trying to describe how to get from O to A using a magnitude and a direction is futile. How would you describe how to get from O to A using a magnitude and a direction? You'd say something like, well, you have to travel at, north, 40 degrees west, a certain distance, and then also another angle, 15 degrees from the ground up to the top. I mean, such a description is possible, but it's so difficult to visualize or understand that how to specify where this point is in 3 dimensions is, I'm not going to say impossible using a magnitude and a direction, but it is ridiculously complicated and hard to understand. On the other hand, how would you describe how to get from O to A using the way that any normal person would? Suppose A is the doctor's office, right? What would you say? How to get to it? You would say go 4 blocks north, go 3 blocks west, and then go to the 2nd floor, right? You would just give the instructions in terms of a up and down movement, a north and south movement, and a west and east movement. And that's exactly how we are going to describe vectors in 3D. You could understand this. Go 4 in the x direction, 3 in the y direction, and 1 in the z direction. And then you would end up where you are. So the reason, algebraic vectors in 2 dimensions, I think, are better. Most of the time, it's better to describe a vector in 2 dimensions using an algebraic vector. To say it's 5x and 10y, as opposed to saying it's root 125 in the direction of north whatever angle east, right? There is a place for those things, so I don't want you to just get rid of them. You still need them, but for most of the rest of the course, we're going to be moving away from them. They kind of stick to Unit 6 only, okay? Especially in 3 dimensions, you're not going to have a lot of success trying to describe a point in 3 dimensions using angles, because what angle are you saying it's relevant to? Is it relevant to the positive x-axis, the positive y, the z-axis? Like, what angle are you talking about? How do you describe an angle in 3D, right? It really can be done, but it takes a combination of angles. It's much easier to just think of it the way you would describe the location of a city, to describe someone's apartment. It's how far left do I go? How many blocks west do I walk? How many blocks north do I walk? And how many floors do I go up when I get there? Right? And that, if you can think of it that way, then remembering how to describe a vector in 3D is pretty straightforward. Anyway, so a vector in 2 space. Now, when we're talking about 2 dimensions, we call 2 dimensions 2 space, and we refer to it as r squared because r, right, is real numbers, and r squared would be real numbers squared. In other words, x is all real numbers, and so is y. So you have all the real numbers in x and all the real numbers in y. You're in r squared. You have 2 axes of all the real numbers. Okay? Any vector in r squared can be written as an ordered pair. Any vector can be written as a combination of an x coordinate and a y coordinate, or an x vector and a y vector if you like. Okay? The magnitude of such a vector would be the Pythagorean theorem. The magnitude of u is a squared plus b squared square rooted, and where a and b are the coordinates, or what we could call the components of the vector. Notice a and b do not have vector signs on top of them because a and b are, the ordered pair notation. So what you would say here is you would say something like, let me just so like this can be written down properly. Uh, just where do I write this? So u, so vector u, oops, right, is equal to AB. Okay, and what this means is the vector could be described as A units to the right and B units up. And of course, if A and B are negative, then it would be left and down, so on. Okay, it has a direction. The nice thing about this is you can always find its direction pretty easily. You just do theta is equal to inverse tan of B over A, where theta is counterclockwise from the positive x-axis. Again, the formula would give you two answers. Of course, the vector only has one answer. It would depend on what quadrant you're in. So, if I'm let's just do a quick example of this. Let's make up a vector. Let's just hide my 3D thing for a sec. Let's make up a vector over here. So, O to no, I don't want that one. How about there? So this vector W. Okay, now the length of W, if I type length W, it comes back with 15.81. Again, how did it do that? It did the square root of 15 squared plus 25 squared. Not 25, sorry, just 5. And that's where it came up with that number. So that's how long it is, right? Just use the Pythagorean theorem on the two components. Now, what direction is it in? So what I'm going to do is I'm going to go inverse tan, okay, of the B over A. And the B, of course, for us is negative 5, and the A is negative 15. Now, when I do inverse tan, it tells me 18.43 degrees. Of course, 18.43 degrees is not the answer, because my vector is in quadrant 3, and it's telling me that the reference angle is 18.43 degrees. So if I want to know the angle here, I got to move it to quadrant 3. So I go 90 plus 90 plus 18.43. So when I draw the angle, so let's make another point A equals 1, 0. And then let's measure the angle between O, A, and C. Okay? And not O, A, and C, I'm sorry. A, O to C. A to O to C. Right? What is the angle it comes up with? 198.43495. Exact same as my answer, but 180 degrees farther than my answer. Right? And again, the thinking there is just, well, my answer, you told me the reference angle was 18, but it's in quadrant 3, so I add 180 to it, and I'm in quadrant 3. Okay, so 198.43 would be the theta of this vector. Okay. Now, the ordered pair AB, you could think about them as a coordinate if you think of the origin, right, as the beginning of your vector. Now, again, not every vector has to start at the origin. In fact, none of them start at the origin. Right? No actual vector starts at the origin, because a vector can start wherever you want it. Again, a vector is like saying walk 3 steps left. Well, what that means to me and what that means to you is entirely different, because we are in different physical locations. But the idea of walking 3 steps to the left is something we can both do and both understand. That's what a vector is. It's just a set of instructions. Now, if we assume that vector starts at 0, 0, then we can say that the point, right, the coordinate or the vector's components point to that particular point. Okay? So for example, if I draw the vector, I don't even think it can do this. Like, look at what it requires to draw a vector. So it says you can draw a vector with just a point, right? So how does it do that? Let's draw a vector to 2, 3. Now, what does it do? It assumes that you meant start at 0 and connect to 2, 3, right? That's what it's going to draw. Now, notice if I put a point over here and a point over here, and then I say vector d to e, as far as GeoGebra is concerned, and as far as vectors are concerned, the vector c and the vector d are the same thing, right? Because they're both move 2 to the right and 3 up. Where you started is irrelevant. That being said, most of the time you're going to want to start at 0, 0. So most of the time, we'll assume that a point if I'm talking about a vector in this form, it started at 0, 0, and it ended at that specific point. Okay, so a Cartesian vector can be written as an ordered pair where the coordinates a and b are the components of the vector. So a is moving left and right, b is moving up and down. Thus, the position vector, right, from O to this point is AB. Now understand the position vector, right, is how to get from the origin to whatever point you're talking about. So a point P has a position vector OP, right? Has a position vector OP. Now, this is where it gets a bit confusing for people. If you say, you would say, so let's say, for example, let's just work with an example. Let's say P is 3, 1. Let's say the point is 3, 1. The position vector, OP, back, right, there we go, okay, is also 3, 1. But try not to mix these things up. Yes, they're both related, but they're not the same thing. A point is not a vector. Okay, a point is a specific place. A vector is a set of instructions for how to move in a certain way. The idea with the position vector, so a position vector tells you how to get from the origin to a specific point. Now, of course, these things are very strongly related. The point is 3, 1, and the position vector is 3, 1, right? So I don't want to. It's just I feel like people mix up what is a point and what is a vector all the time, and it really throws them off later in the unit. So if it feels strange that I'm making such a big deal of this, just try to bear with me and understand that this is an important thing to understand. How does GeoGebra handle this? If I type in 3, 1, okay, it assumes I meant a point. Right? If I say q equals 5, 2, it assumes I mean a point. However, if I make q lowercase, now it draws a vector. Right? And the vector it draws goes from the origin to point q. So of course they are related and they are very similar. And the vector OQ, right, is the same thing as the point q in some ways. It's because it's how to get there from the origin, right? But they're not the same thing. And if I want to sort of do calculations on them, I need to be careful that I'm making sure I know the difference. So anyway, on GeoGebra, when you want to draw a vector, use lowercase. Vector v is 10, 1. If I want to use a point, use a capital letter. Okay, and of course you can always manually override this. You could say capital V is vector O to Q, right? And then you could still name a vector a capital, but it's just not going to do that by default, okay? Okay, now, the other thing that's really helpful to understand is that any vector you want can be written in the following format, okay? Vector I is equal to 1, 0. Vector j is equal to 0, 1. Some combination of I and j must be able to express any vector imaginable in 2 degrees anyway. Let me demonstrate this quickly. So here's a and b, and I'm going to draw a new vector v, which is a times j, or a times I, sorry, j, a times j plus b times I. Okay, yeah, whatever, it doesn't make a difference. So if you were to alter your values here, right, you must be able to find a way to get this vector to point to whatever you want, right? So the concept is any vector in 2 dimensions can be expressed as the sum of a certain amount of vector I and a certain amount of vector j. Okay? Vector I is a unit vector. It has a magnitude of 1. That's why it has a little hat on it instead of a vector sign. Okay? So again, just to clarify this one, it's I hat, I hat bracket equals 1, 0, right? And j hat bracket is 0, 1. And any vector is equal to some combination of I plus some combination of j. Right? Because just for the same reason that it can be described as a point on the plane, it can be described as some combination of as the sum of I and j. There isn't too much to remember about that. Just try to remember I is a unit vector in the direction of x, j is a unit vector in the direction of y. Okay? Oh, I see what's going on. I'm just trying to copy paste this for the notes so that it's consistent. Okay, so anyway, so here same thing. A and B are their scalars here. Any algebraic vector can be expressed as a scalar multiple of the unit vectors I and j. Okay, really important. This is something I could ask you to prove, right? So in communication, let's say prove it, right? And what you would do there is you would just say, you know, since any vector can be written as two components, and one of those components is a scalar multiple of I, and the other component is a scalar multiple of j, adding them together, you could express any vector as some amount of I plus some amount of j. So all of these things are the same. They're just different ways of knowing how to do it and different ways you might see it. So ordered pair notation and unit vector notation are the exact same thing. You can either say A comma B, or you can say A times unit vector I plus B times unit vector j. These just mean the exact same thing in every way. Okay, and again, I might ask you in communication to just, why are these things equivalent? Or, how is this statement related to this statement? That kind of thing. Okay, now, when you are drawing a vector in 3D, okay, so in R3, so R3 would be real numbers cubed. There's an x-axis of all real numbers, there's a y-axis of all real numbers, and now there is also a z-axis of all real numbers. Okay? Again, the far easier way to describe a vector in 3 dimensions is to talk about it in terms of its components, in terms of its coordinates. To think of it as a position vector that starts at O and terminates at some point. Okay, again, an angle and a magnitude, hopeless, right? It just you could describe it for 10 times as much time and the person still wouldn't have as clear an idea as if you just explained it this way. So this is the way we're going to be doing it in 3D. A couple of things about 3D. Okay, the z-axis is the up and down axis, so it is the vertical axis. Okay, it's customary to write the y-axis as the left to right one now, so y has kind of changed with x. Positive z is going upward, positive y is going to the right, and positive x is coming out at you towards the page, like towards you, out of the screen, right? So just one more time, z is pointing up, y is pointed to the right, x is pointed towards you, or what we say out of the page. A negative x is pointed into the page. Okay? So again, A, B, C are the coordinates of P, so you can do the same thing with a position vector. You can assume you're starting at 0, and therefore the location of OP the vector is just the 3 coordinates. They are the components. Again, you can do the unit vector thing. Vector I is 1, 0, 0, because you move 1 in the x, none in the y, none in the z. Vector j is nothing in the x, 1 in the y, nothing in the z. And vector k is nothing in the x nor y, 1 in the z. So some combination of those 3 vectors must be, you must be able to express any point in 3 dimensions. And again, I would just say, you can describe any point in 3D, like think about a position in the school, right? You have to go a certain amount left and right, a certain amount north. Left and right's a bit confusing. Let's say a certain amount north and south, a certain amount east and west, and then a certain amount up and down, right? And that you could find any location in a city doing that, right? If you want to address something to a person who lives in an apartment building, you give them their x and y coordinates, which is the street that they live on and the address, and then you say the floor number, right? And that would be sort of like their z coordinate. Okay? Now, interestingly, the magnitude of this vector is kind of like a triple Pythagorean theorem. A squared plus b squared plus c squared, all square rooted. We'll go through why that works a little bit later, but you can still find the magnitude. It's still quite easy. You just take the three components, square them all, and then root the sum. The other thing it talks about here is a plane. Now, I'm going to explain planes, but I'm going to do it a little bit further down when we have access to the better picture. So let's just, for the time being, try to think of a plane like a sheet of paper. It doesn't have any thickness. I mean, obviously a real piece of paper does have some thickness, but a piece of paper doesn't really have a thickness, but it does have two dimensions, right? It has a left and right dimension and an up and down dimension. Once again, whether you write it as an ordered pair or a unit vector sum, it doesn't matter. A, B, C is the same thing as AI, BJ, CK all added together, so that's fine. Now, how to draw in 3D is the first thing that we're going to practice, and it's going to be a bit tricky for me to do this with you because I don't really have good access to something that could let me draw. So here's what I'm going to suggest you do: draw a normal, axis on your page, like a normal up and down one, a left and right one, and then you draw a diagonal one like this, where the front half of it is filled in and the sort of back half of it, if you like, is dotted to show that it's going into the page. Okay, now let's label this thing. This is the negative x direction. Okay, this is the positive x direction. Let's put x in red just so we can. Okay, that's the x direction. Okay, now the y direction would be this one. So let's put y direction in green. So there's the y direction. It still works the way the old x used to. So positive y is over here, and negative y is over there. Okay, and just sorry for consistency, we'll just make these also green. And finally, we have the z direction. Okay, which will make a positive z, which would be going up, and a negative z, which would be going down. Okay, so this is how you are going to draw your axis. And again, just get rid of the label for this. Get rid of the label for this. And I don't actually think we need the numbers. I think the numbers are probably just going to be confusing, so let's just get rid of the numbers. Okay, and let's make the z-axis blue. Oops. Sorry. Interesting. Doesn't let me do that. Okay, blue. Okay, so here's what your page should look like. So it should look like a regular axis with the z and the y, and then you kind of have this axis on an angle with the z, with the x, I'm sorry. Now suppose we wanted to draw a vector here. Let's say we're supposed to draw, let's see, now I'm going to come back to that. Let's say we're drawing this one here. So we're supposed to draw, actually this is a bad example because it doesn't have a, let's go to this one. 1, 3, negative 4. Okay, so suppose we had to draw 1, 3, negative 4. How do I do this? First, I want to draw the 1 along the x-axis. So to draw the 1 along the x-axis, basically I want to move 1 unit along this axis going forward. So what I'm going to do here, let's make a quick, I think this might just make it slightly easier to understand. Negative k, k from negative 10 to 10. Okay, I think that's good, but let's zoom it in so they're not so, oh right, okay, sorry. Just don't want to lose all these things. I'm just thinking it might be helpful to actually see some dots on that so that there we go. Okay, now let's make these points all red because they're x-axis points. And is there a way we can make them smaller? Yeah, beautiful. Maybe not that small. Okay, so here's my drawing, right? And I've got a tick mark on all the x's and y's, right? So there's a tick mark on all the y's, tick mark on all the z's, and now a tick mark on all the x's. So suppose I want to draw this coordinate 1, 3, -4. How do I do that? First, draw just the x. So here's the x, right? So you can see I've got a little vector. I'll draw the x vector first. Now again, just ignore the fact that mine says 1, 1 because I'm drawing it in 2D even though I'm drawing a 3D thing. So the numbers here are not relevant. It's just try to concentrate on what I'm drawing as if I was drawing it on a piece of paper. Okay. So I've drawn the x part. It was 1 unit in the x direction. Okay. Now let's get rid of the label for this. Okay. Now the next thing I'm supposed to draw is 3 in the y. So I'm going to go over to the y. I'm going to go 1, 2, 3 tick marks over, and I'm going to draw that. So I'm going to go vector OC, and let's get rid of that label. And so I've drawn the x part of the vector, if you like, and the y part of the vector. Now the last thing I'm supposed to draw is a -4. So in the z direction, I'm supposed to go down -4. So let's do that. And then let's draw vector OD. Okay, and that, I now have the 3 components, if you like, for my answer. 1 in the x, 3 in the y, and then 4 down in the z. Now, to draw this, to finish drawing it, okay, what you need to do is you need to follow all 3 of these vectors as though you were adding them together. So observe what I mean. If I said, I'm going to draw them as if they're, so just follow it with my mouse for a second, then we'll show. Imagine I started at 0, 0. I went 1 unit in the x direction. That got me to A. Then I went 3 units in the y direction. That got me to A plus C. And then I went 4 units down in the z direction, and that gets me to my answer. So my answer is going to be somewhere down here, right? Now, again, let's sketch the full box. I often find this box is helpful for drawing this. So let's draw a quick box here. So what I'm going to do is I'm going to take this vector here, and I'm just going to shift it down so that it starts at A. So I'm going to go vector A and A plus that A, right? And then I'm going to go vector A plus C and then to C. So you kind of see what I'm doing here. I'm kind of like drawing a little 3D box, and I don't want these ones to be oh, I see. I misunderstood that. Yeah, no, actually this is fine. Let me leave it the way it was. Let's go from C to A plus C. Make this a bit easier. Okay, so if you were to just do A and C, you would end up right here, right? And you can see it's kind of like the parallelogram we were talking about last unit. I could do this vector first and then this one, or I could do this vector first and then that one, but I would still end up in the same place. Okay? Now suppose I wanted to add the last vector here, right? So the last vector would be vector A plus A to A plus B. Okay, so this would be where my vector actually ends. And to answer the question, I would just draw a vector from the origin to that spot. And this here is my answer. Let's rename it to U, because often the answer is U here. Let's get rid of all the labels for the other ones. Okay. Now, so the answer here is what I've drawn in U. Now, how did I get there? Let's fill out the rest of this thing. So you could set what I said was draw a box, right? So let's continue the box. What if I went C first and then I went down? Where would I be there? So I want a vector that joins C to C plus, I called it B, right? So I have that one. Then I want a vector from that one to the destination. Oops, sorry, what was the original one called? D, right? So it's kind of like I could also have gone over to the right, then down, then forward. And I would still arrive at the spot where I'm trying to get to, right? I would still arrive at this point E. Okay? Now another path you could go is down first, then out, and then over, right? Or down first, then over, and then out. So there's no limit to the number of ways this can be done, right? Let's go vector d to d plus 3, 0. You could go that way. Vector d plus d. You could come out that way. Vector a to a plus 0, negative 4. Sorry, not d plus a plus 0, negative 4. You could go that way. And finally, you could go down first to get here, then out towards here, and then over, right? So that would be vector d plus d. So that gets me down to the bottom left corner. And then I would have to go d plus d, and I need to add another vector going to the right, which was, I forget what it was called, but it was 3, 0 anyway. Let's get rid of all of these labels. E, I'm just going to get rid of the label for E. Okay. Now, my answer to the question, all you need to do to answer the question is draw the vector to U. Right? Draw the vector from F to U. Really, all these other ones I drew, you could just these ones could just be dotted, right? Like they don't. Right? And so same with these ones. They're all just. Right? So, oh, sorry. U is the actual answer. So let's make that one thicker and solid. Okay? So the answer is, describe this point. Well, it's 1 unit towards us, 3 units to the right, and 4 units down. Again, how you get there is up to you. Any order would work. You could come forward, then right, then down. You could go right, then down, then forward. You could go down, then forward, then right, etc. There's different ways of getting there, and any one is right. So my advice would be draw the 3 original vectors, okay, and then start at the beginning, follow one of the vectors, draw the next vector and follow it, and then draw the third vector and follow it, and you'll always get to the answer. Okay, so that's how you draw one in 3D. Again, this is not a skill that we need to, this will be like a 2 points in communication, right? Just to show me that you know how to do this. It's not a lot of our work actually involves drawing them. So if you find this difficult, it's okay. Many times when you want to visualize something, you'll have a much easier time if you just go to 3D graphics, right? Of course, this is all nonsense. I didn't actually draw a 3D thing, right? I drew a 2D thing. If we actually find the location of this point, actually, sorry, I do want to save this, so let's make a new window. Sorry, that 3D thing was not a good idea. If we want to actually find the location of this point, so it was 1, 3, negative 4, right? Just go to the 3D graphics view, and you can see, okay, so red is X. The point is a little bit towards us, right? Because it's towards positive X. It's off to our right a little bit in the Y direction, and then it's negative in the Z direction, right? So that would be where that point is. Now again, it takes some getting used to this, right? This is difficult. It's hard for us to visualize 3D things as easily. We just don't have the same experience. Obviously, in the real world we do, but in mathematics we don't. So just try to use this. Use GeoGebra's 3D view, right? I use GeoGebra 5. It's my preferred. I think it's better than 6. You don't have to use it. You could use 6, but whatever. And just go to the 3D graphics view. This is really, really helpful for the remainder of this course, okay? Anyway, let's go back to what we were supposed to do. So we learned how to draw. One. Okay, so give it a try. See how it works. Now let's prove this now. The magnitude. How do you get the magnitude? So let's find the magnitude of the vector from O to A. So let's go O equals 0, 0, 0. And then OA is the vector from O to A. Okay, so that's what we were drawing. That's what we've got, right? Now, how do you get the magnitude of that? If I say length OA, it comes back with 5.1. Now, how did it get 5.1? To do this, what I want to do is look at it in 2D twice. So let's look at it as though we are looking straight down. And if when we're looking straight down, you notice I can't see the z-axis anymore because it's coming right out at me. And the point, I can't tell that the point is actually below because as far as I can tell, it's just sitting on the axis, right? Now, suppose we were to calculate the x and y distance across to the point above where A is, right? So let's draw a new point, A prime, A prime, and let's make it directly on top of A, but with no z coordinate. Okay, so it's directly on top of A, and you can see that when I look at it from above, A and A prime just look like they're in the same place. Now, how far away is that point? Well, we know that that point is it's 1 unit away in the x and 3 units away in the y, right? So if we just draw a triangle, OBA, let's say polygon. Okay, if we draw that polygon, we can figure out. Oh, I'm sorry, not A. My mistake. Not A. I want A prime. I want the one that's on the. What? Okay, right. So there's a 2D triangle that's not taking into account the z-axis yet. But you can see that to get from O to A prime, you would just do the Pythagorean theorem. You would do 3 squared plus 1 squared, and you would do the square root, and you would get 3.16, which is the length of that segment, right? So 3.16 gets me from O to A prime. Now, let's look at the thing again, except this time let's look at it directly from the side so that we have this second right triangle. And let's draw a polygon, OA, A prime, right? And now we have a second triangle. So we have it's like one triangle was vertical when we were looking at it vertically. The second triangle is when we're kind of looking at it in profile. Now this second triangle, it has a opposite of 4, so 4 squared, and it has a adjacent, the thing across the top, of the 3.16 that I got before. So 4 squared plus 10 squared, plus just 10, so c squared, right, gives me 26, and then I do square root of e, and that gives me the 5.1, which is the magnitude of my original vector. So this is just a demonstration to hopefully help you understand why does the Pythagorean theorem continue to work in 3D, and how come we can just stick the third point on there. Okay, the a squared plus b squared gives you the hypotenuse of the 2D triangle, and the hypotenuse of the 2D triangle is just the adjacent of the 3D triangle. And then you add the opposite, and you do this one squared plus this one squared to get the magnitude squared. Okay? Try it on a piece of paper yourself. I think you'll be able to prove that. Okay, direction angles. Now, again, describing something with angles in 3D is not very wise, but there is a way to do it, and there'll be at least one question where you're just asked a little bit about how to do this. So there are 3 things called direction angles, and basically we're going to describe a vector as having 3 angles at a time. What angle does it make with the x-axis? What angle does it make with the y-axis? What angle does it make with the z-axis? Okay? Now, always we are going to define these as a number between 0 and pi because we don't want to go a full rotation. We're just going to take the 1/2 angle. If it goes over to the other side, then we're just going to take the angle on that side. Okay, so it's the angle with the positive x, y, or z axis. Okay, and how you get them is you just each coordinate. So the x coordinate over the magnitude would be the cosine. The y coordinate over the magnitude would be the cosine of beta, and the c, or the z coordinate, over the magnitude would be the cos of gamma. Okay, so let's just, I think I can sort of quickly show this if we, let's draw the same one again. So 1, 3, negative 4, vector OA. Okay, so there's my vector. Now what angle does this make with the positive x-axis? So I'm going to draw a new vector I, which is 1, 0, 0, and I'm going to go angle UI. Now you can see it makes a 78.69 degree angle with the x-axis. Sorry, I'm having trouble actually showing this, but because I think I have it upside down, so it's not spinning the way I think it should. Okay, right? So there's the angle it makes with the x-axis. How did I get that? I did inverse cos of the magnitude, so of the x-coordinate, which is a 1, over the magnitude of vector u. The magnitude, remember, was root 26, right? So 1 divided by square root 26, and then inverse cos of that number is giving me this 78.69. Now, let's make a vector in the y-axis. We'll call it vector j, 0, 1, 0. Okay, and let's measure the angle between j and u. And that angle, so again, I'm going to hide the x one just so this is not hopelessly. Okay, the angle it makes with the y-axis is under there, 53.96 degrees. How did I get that? 3 divided by square root 26, and then inverse cos, of b. And you get 53.96. The last one we know is going to be inverse cos of negative 4 over square root 26. Gives me an angle of 141.67. And if I draw a vector, let's call this vector k, is 0, 0, 1. So it's parallel to the z-axis, is pointing up. And I check the angle between k and u. It gives me this 141.67 degrees. Now, again, you could describe the location of point A as it is, root 26 units away from the origin at an angle of 141 to the positive z, 53.9 to the positive y, and 78.6 to the positive x. But the time it would take for a person to comprehend what you just said is just often this is not a helpful way to actually describe where a vector is. That said, I want you to know how to do it, and I want you to remember this identity down here. Okay? This is actually quite useful. You can create a unit vector in the direction of u by dividing each component by its magnitude. And if you do that, you must get cos A, cos B, cos gamma, cos alpha, cos beta, cos gamma. And since it's a unit vector and has a magnitude of 1, that must mean that if you square and add all those cosines together, you get 1. Let's demonstrate that here. So my angles, just quickly, was alpha. Let's just rename the other one. So I'm going to rename this one to beta, because it's supposed to be beta anyway. Beta, and this one was the gamma. Okay, so gamma. Okay, now if I say alpha cos alpha squared plus cos beta squared plus cos gamma squared, I always get 1. Okay, so remember this. Just put a note beside it, and just make sure when you're studying, when you're studying for the test, come back to page 3 or whatever. Sorry, I don't know what page this actually is. It looks like page 4, but anyway, come back to this page and review the direction angles and the special identity. It doesn't come up very often. It's not something you're going to be using every question. It's easy to forget, so just come back to it. Okay? It says draw the position vector of each of the following points. Find the magnitude and direction with the x-axis. Okay, so find the magnitude and then find the direction with the x-axis. So A is fairly simple. A is a two-dimensional vector. So draw a position vector. I'm not going to draw it. I'm going to trust you to draw it. The magnitude equals -2 squared plus 5 squared, and all of that either square rooted or, to the power of 1/2, right? Would be another way to do that. So what you're going to get here is square root, the magnitude is square root 29. Okay, because 5 squared is 25, -2 squared is 4, and you add them together, you get 29. Now, the magnitude, the direction with the x-axis. Okay, so let's write direction with x-axis is, what does that mean? We called that one alpha. Just make sure I get the same thing. Is alpha, and alpha is equal to, okay, so to get alpha, you say cos of alpha is equal to the x-coordinate, which is a, divided by the magnitude, which is, p vec divided by the magnitude of vector OP. Okay? All right? So in our case, how do you get this? You take -2, you divide it by the square root of 29. I was hoping that would work. Should have tested it. Oh, it might be square root, actually. I should try that after. You take this, right? And you take that number, you do inverse cos of this, and this is all there ever is to it. That tells you what alpha is. Okay, so in our case, let's just quickly draw this one. So I'm going to just reset all this stuff. Okay, so let's say A equals -2, B equals 5, C equals 0. There's no Z in this one, right? It's just a 2D question. So then what I'm going to do is I'm going to draw a vector O to A, B, C. Okay. Draws vector U. There it is. I'm going to make vector I 1, 0, 0. That's the x-axis. Vector j is the y-axis, 0, 1, 0, or is parallel to the y-axis. Vector k is parallel to the z-axis, and so on. If I want the angle between u and the x-axis, I get 118.8 degrees. And this should be doable just using like a advanced function style trig, because you're just doing a 2D question here. But again, where does this come from? Inverse cos of -2 divided by square root of 29 gives you that 111.8, right? So that's where that's coming from. Okay? So we found the magnitude was root 29. The direction with the x-axis we found to be 111.8. Okay, so that's its direction with the positive x-axis. Next question is the same thing, except this time the magnitude is equal to square root 5, and the alpha is equal to inverse cos of 1 over square root 5. And alpha, therefore, is equal, let's just quickly change this one. So A is 1, B is 3, B is -2. Okay, so again, the angle with the positive x-axis, which is the positive red, so like if we're used to seeing this, we're used to seeing it like this, I guess, where positive x is to the right, positive y is up, negative x is to the left, and negative y is down. The angle with the positive x-axis is 63.43 degrees. And again, that you would get that by doing inverse cos of 1 divided by square root 5. And you get the 63.43. Okay, last one we already did, but just quickly review how to do it. So the magnitude would be, yeah, right, it does that, but does it work with? No, not very useful. Okay. Okay, it would be so it would be the 1 squared plus 3 squared plus negative 4 squared would be the magnitude. So again, what happens when you actually do this? You get 1 plus 9 plus 16 equals 26 equals square root 26. Since we need to root it, right? Oh yeah, it does work. There you go. Not sure why it didn't get rid of my brackets though. Okay, square root 26. Okay, so that's the magnitude. Then we would get the alpha. Very straightforward again. Alpha is equal to inverse cos of the x coordinate, which is a 1, divided by square root 26. Alpha is equal to, let's just do 1 divided by square root 26. And then inverse cos of that, 78.69 degrees. Again, to just demonstrate this one, A is 1, B is 3, C is negative 4. If I were to check the angle between U and the x-axis, I get 78.69. And again, that angle is like, you take the positive x-axis and my vector, and you measure the angle in between them. You get 78.69. Okay. Now, one of the big challenges of 3 dimensions is how to describe a plane. A plane, try to think of it as like a surface where you can move in 2 directions but not a 3rd direction. Try and visualize the classroom. Okay, close your eyes and think of the classroom. Underneath you and above you, you have the floor and the ceiling. Okay? The floor and the ceiling, you cannot move. If you moved up or down, you would exit that plane, right? So on the floor, you can move in an x direction, which is forward and backward. You can move in a y direction, which is left and right. You cannot move in a z direction, because if you moved in a z direction, you would leave the plane. Okay, so this is the way I try to think of it. Okay, you try to think of it as a classroom. Okay, the floor or ceiling equals the xy plane, and there is no vertical movement on these planes. Okay. On the other hand, the smartboard at the front of the class is the YZ plane. There is no forward or backward movement. You cannot move into the board or come out of the board. If you were to do that, you would no longer be on that plane. Finally, you have the wall with the door or the wall with the window. In our case, for this year anyway, the door is on our right, the window is on our left, but it doesn't matter. Both of these are the same plane. They are the XZ plane. You can move forward and backward. You can move up and down, but you cannot move left and right. Because if you move left and right, you wouldn't be on that plane anymore. Okay, so that's the way I try to think of this. Okay, it's like a surface, and the easiest way to think of a surface is like the wall of a room. Okay, so I would be on the wall of the room where the smartboard is if I moved up and down or left and right. But if I moved forward or backward, I would leave that plane. Right, I would no longer be on that plane. Where would each of these vectors be located? Well, look at this first one. You can move forward and backward. You can move left and right. You cannot move up and down. Forward, backward, left and right, no up and down. Forward, backward, left and right, no up and down. There is no up-down movement in any of these vectors. Let's draw them quickly just so we can reinforce what I'm talking about here. So 1, 2, 0, 3, 4, 0. And negative 2, 0. Okay, now look at where those 3 vectors are. They are all on the floor, if you picture this as the floor, right? None of them move up or down in any way, right? They're all on the floor, and the floor, we said, is the xy plane. This is the xy plane because there is no z movement. Now again, the same argument would be here. I will draw these ones, but I'm not going to bother with the third one. But let's draw these ones so you can see. So this one was 0, 1, 1. This one was 0, -3, -4. This was 0, -2, and +2. Okay? Now, look at this stuff. There's movement left and right. There's movement up and down. There is 0 movement forward and backward. Right? All three of those vectors lie on the same plane because there is no movement in the x direction. So this we lie on the yz plane. Notice all x values are 0. This one obviously is going to be the xz plane, no y movement. So no left or right, only forward, backward, or up and down. Okay? This is a really good visualization exercise. Try to think a lot about this. Okay? Visualize it, draw it out, describe things in your room using these terms. Just try to get used to thinking about things in this way. This is hard to visualize, but you can train yourself to improve. Okay. Let's finish up here because this one's gone quite long. It's a lot to think about today. So let's just go through these last ones quickly and we'll. So it says express each of the following in ordered pair notation. Okay, 5a plus 6j. That would be equivalent. Let's write it out the long way once, and then we're not going to write it out the long way again because again it's tedious. But okay, 5. So what would happen if you took vector j? So remember, what is this underline? Remember, I'm not going to bother with the vector sign. 1, 0, 0. J is 0, 1, 0. So what would happen if you were to add 5 times 1, 0, 0 plus 6 times 0, 1, 0? Well, you would get 5, 0, 0 plus 0, 6, 0. And when you add those two things together, you would get 5, 6, 0. Okay? This is what is so powerful about components. Look how easy it was to add vectors together. I didn't take any cosines, I didn't draw any pictures, I didn't, it's so much easier to add vectors together when they are written in ordered pair notation because all you have to do is add each x to each x and each y to each y. Okay, let's do this. Obviously now you can see there's also a very fast shortcut to doing this. The shortcut is simply -4i would be a -4 where the x goes. -3k would be a -3 where the z goes. Recall that k is 0, 0, 1, not k is the z vector, right? 4j, let's use the same idea. 4j, again, let's just do it the simple way. There's no x's. There's 4 movements in the y direction, and there's no movement in the z direction. So again, you don't need to do this where you write them out and add them up. I just want to show you how that works. You can just skip right to this, no problem. Okay, if u is ai plus 5j minus 3k, and v is b negative 15c, and they are parallel vectors, find c and the relationship between a and b. Okay, so let's write this out. Vector u, let's write it it would be a5 negative 3. Okay, vector v would be equal to b negative 15 and c. Okay? So let's just review. So it tells me v in that form already. And then vector u is I'm just converting it to this form. Now, according to our equation, parallel vectors means that u can be expressed as kv. Oh boy. Okay, u can be expressed as kv. So think about how that would work. That would mean that each component, if the two vectors are parallel, then all their components need to be parallel, right? So let's break it down and go component by component. A, so let's talk about the x components first. A equals kb. In the y coordinate, 5 equals k negative 15. In the z component, negative 3 equals kc. Now obviously you want to start here with the y coordinate because it says from here you can solve that k equals negative 1/3. Because if I take negative 1/3 and multiply by 15, I get 5. So that tells me that these two vectors, if they're parallel, then this equation must be true. And if k is negative 1/3, the equation is true. So I go back here and I say c must be equal to 9, because 9 times negative 1/3 is equal to negative 3, right? You just isolate for c. And here, I can't actually solve this one, but I can say a is equal to negative 1/3 b. I do know that. As long as I have that, then the two vectors are parallel. Okay, and that's all it's asked me to do, is just get the relationship between a and b, so I can say a is negative 1/3 of b. Okay, please try this stuff. Reach out if you have any questions, or if there's anything here that just needs to be explained differently or better. I'm doing the best I can with this, but of course, if something is not making sense or you're struggling, ask me, right? I'm happy to give it another try or see if there's something else I can do for you. Okay,